The last set of topics in this section, which is pretty consistent with the way we do most of the discussions in this course, will summarize the usage considerations to keep in mind when you attempt to apply Java semaphores in practice. So the thing to remember is that a semaphore is a lot more flexible than other simpler Java synchronizers, in particular reentrant lock. We haven't really talked a lot about that yet, but you'll learn more about it shortly. So semaphores are more flexible than reentrant locks, and they're also more flexible than synchronized statements. That obviously is not really me, but thanks to Photoshop, it looks like me. One of the things you can do with a semaphore that you can't do with other types of synchronizers is you can atomically acquire and release multiple permits with a single operation. We haven't really talked about that, but you can do that. So you can get a bunch of things all at once. Also, its acquire and release methods need not be fully bracketed, as we just saw with the example of the ping pong program that alternates printing ping and pong in different threads. Now, because of the fact Semaphore is more powerful, you should not be surprised that with this power comes greater overhead, to paraphrase Peter Parker's uncle or aunt, depending on which version of Spider-Man you watch. So the flexibility comes at some additional cost and performance. So if you're just trying to do very simple synchronization things like provide critical sections where code can't be interrupted by multiple threads running at the same time, stick with a simpler synchronizer like a reentrant lock or a synchronized statement. But if you need this additional flexibility, then Semaphore could be what you want to apply. When a semaphore is used for a resource pool, it tracks the number of free resources. And this goes back to a discussion we just had when we were talking about mediating access via a semaphore. It just tracks the number of free resources. However, it doesn't track specifically which resources are free. So think back to the example we talked about before. The semaphore is used to make sure that only n threads are accessing n resources in the resource manager, in the Palantir manager. But it doesn't know, the semaphore doesn't know which particular Palantir are available. That requires something else. And what that typically requires is some other mechanisms to select the free resource. So some kind of list, some kind of hash map. And of course, you need to make sure that those things are properly synchronized so that they don't get corrupted when multiple threads are inside that critical section. So again, semaphores are often used in conjunction with other types of synchronizers to provide holistic solutions to things like current resource management problems. And as I said, these mechanisms, like these collections and so on, require synchronizers to ensure thread safety. Sometimes they come for free. Some things like concurrent hash map are already done that way. Sometimes concurrent queue, linked queue already has that, but other times you have to do it yourself. Now, something else we have to talk about, if we're being candid, is that semaphores can be tedious and error-prone to program due to various common traps and pitfalls. So here are some examples of things that can go awry and get you into trouble. One problem is holding a semaphore for longer than you need to. So you can't let other threads can't get in to do their thing. Here's a very simple example. We have a semaphore which starts out with the count of 1. We come into some method, we acquire the semaphore, and then we do some long-running computation. It has nothing whatsoever to do with the semaphore, and when we're done, we release the semaphore. Well, any other threads won't be able to acquire the semaphore while we're sitting here doing something that's unrelated. So that may not be the best use of those threads' time. So we probably need to think about how do we refactor the code. Another problem is releasing the semaphore more times than you ought to. So here's a case where we acquire the semaphore, which drives its count to 0, and then later we release it 3 times, which will cause chaos and insanity because then it'll have all kinds of other threads able to acquire resources that may in fact not exist or may not be available. And this, of course, this example is contrived, but you can imagine an example with complicated if-else statements and control flow and so on where that could happen. And there's nothing in the Semaphore API that will prevent you from doing this. It's perfectly happy to keep releasing the semaphore and incrementing the count by 1. Another problem is to acquire a semaphore and then forget to release it somewhere. So here we have a semaphore with a value of 1, and then we go ahead and call acquire, and then somewhere along the way we return, and we had intended to release the semaphore, but the return causes the semaphore not to be released. And this is also why you would want to use try finally blocks to make sure that doesn't happen. So this would be an example of how we could use the Java try finally idiom to ensure that a fully bracketed semaphore is always released, even if exceptions occur. And if you think about it, that's actually very similar to what you did in the acquire, palantir, and gaze hook method from assignment 1A, where we used the try finally block to make sure that we always released the resource, the palantir, even if an exception occurred. Semaphores are rather limited synchronizers that don't scale to complex coordination use cases. So if you have something that's really complicated, semaphore may not be what you want. It might be more appropriate in such cases, maybe, to use Java condition objects, which are another type of synchronizer we will talk about later, that are perhaps a better choice for complex coordination use cases. So that's the end of the overview of Java semaphore usage considerations.